So we have seen numbers, we have seen natural numbers, we have seen integers, rationals, reals, and we have loosely talked of them as sets of numbers. So let's try to understand a little more clearly what we mean by a set. So at its basic level, a set is a collection of items. So for instance, we could have a set called the days of the week, which has 7 members: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. Or we could take a number like 24 and list out the factors of 24 and call this a set. So we have 1, 2, 3, 4, 6, 8, 12 and 24. So if you count, there are 8 factors that 24 has. Or we could take all the prime numbers up to a certain limit. Supposing we want to know the prime numbers below 15, then we know that we don't have 1, but 2, 3, 5, 7 are the single digit prime numbers, and then 7, 11 and 13. So 2, 3, 5, 7, 11, 13 are all the primes below 15. So this is how we talk about sets informally, as just collections of items. Of course, as we have seen, sets can be infinite, and in particular the infinite sets that we deal with very commonly are those which consist of the different types of numbers. Remember that n, this funny n, stands for the natural numbers, that is 0, 1, 2, 3, 4. Z stands for the integers, so that's the natural numbers along with the negative integers like -1, -2, -3 and so on. Q is a peculiar symbol for the rational numbers. These are the fractions, those numbers which we can write as p divided by q, where p and q are both integers. And finally, R is a set of real numbers. So the real numbers includes all the rationals, all the fractions, but also numbers that cannot be represented as fractions, such as the square root of 2 and other irrational numbers like pi and e. So in all these things that we have seen above, it looks like there is some kind of condition which requires a set to have some uniformity. Either a set consists of numbers or a set consists of days of the week or something like that. But actually, mathematically, there is no constraint on this. A set can have any kind of members, even a mixed membership. There is no uniformity of type. So for instance, we could enumerate the set of objects that appear in a painting. Now here is a particularly famous painting where it's not so easy to enumerate the objects because it's drawn in a very abstract way. This is a painting called Three Musicians by Pablo Picasso. But we could see roughly that there are 3 people in that, there are some musical instruments and so on. And if you look very carefully, you will even find a dog. So notice that there is no commonality. There are people, there are musical instruments, there are chairs, there are tables, there are animals and so on. So a set in particular can have any kind of members. It doesn't matter if they are mixed in type. So one of the important differences between, say, a set and a sequence or a list is that the order in which we identify a set doesn't matter. So normally when we talk of numbers, we tend to list them in a particular way, but as a set, it doesn't matter. So for instance, if you take the set of cricketers Kohli, Dhoni and Pujara, if you reorder the set as Pujara, Kohli and Dhoni, it is the same set. Right? So the sequence in which you list the members of a set does not matter. And for that matter, if you happen to accidentally write the same member twice, it doesn't change the set. So in this particular set, if we add Kohli a second time, as a set it doesn't matter. Though of course, if you are a cricket fan, maybe you would like Kohli to bat twice for you. So when we look at a set, we might ask a basic question as to how many members it has. So the cardinality of a set is the number of items in the set. And if it is a finite set, we can just count the items. So for instance, if we look at the factors that we listed of 24, then we can count them and say that this has cardinality 8. Sometimes it may not be obvious that a set is finite. You might remember from geometry that a regular polygon is one where all the sides are equal and all the angles are equal. So the smallest regular polygon is an equilateral triangle in which we have 3 sides all equal and 3 internal angles of 60 degrees each. Then we move to 4 sides, we get a square. Then we get regular pentagons, hexagons, heptagons, octagons and so on. So for any number of sides, you can draw a regular polygon with that many sides with equal angles on the inside. So there is no limit. The set of regular polygons is infinite. But if we move to 3 dimensions, the corresponding notion to a regular polygon is what is called a Platonic solid. In a Platonic solid, first of all, you have surfaces or sides. Each side is a regular polygon and all these regular polygons meet at the same angle in 3 dimensions. Now it turns out that though you might imagine that there are infinitely many regular polygons in 2 dimensions, there are only 5 Platonic solids in 3 dimensions. So this is an example of a set which turns out to be finite even though there is no reason for it to be finite. So these 5 Platonic solids are the tetrahedron which has triangles, the cube which we have seen which has squares, and then we have an octahedron which has 8 sides which are triangles, then we have a dodecahedron with 12 sides and an icosahedron with 20 sides. And there are no other regular solids, surprisingly it turns out. Now cardinality is quite easy to determine for a finite set, but what about for an infinite set? Remember that we said that we wanted to go from integers to rational numbers because we wanted to talk about what happens when we divide 2 integers and the answer is not an integer. And it is clear to us from our discussion that integers were discrete. We can talk about a next number and a previous number. So there are gaps in the integers, and rational numbers were dense. Between any 2 rational numbers, there is another rational number. So intuitively, it seems like we are adding things to the integers to get rational numbers. But can we make it formal in terms of cardinality? Are there more rational numbers than there are integers? And what happens when we go from Q to R, when we go from rational numbers to real numbers? So remember that the real numbers we had to introduce because there were numbers such as the square root of 2 which could not be represented as a fraction. So clearly there are some rational numbers which are real and some real numbers which are not rational, and therefore we have a bigger set. But again, is R really bigger than Q? So this is a separate discussion. There will be a small separate lecture about this, but there is a way to measure cardinality of infinite sets, but it is not as straightforward as it is for finite sets, as you would imagine. So how do we describe a set? Well, we have already seen that for a finite set, we can just list out the members of the set explicitly. So we can write out 3 numbers, Kohli, Dhoni, Pujara, or 8 members, the factors of 24. So the normal notation for a list of items which form a set is to use these curly braces and to separate the items by commas. Now in many books and even in our lectures, we will see notation like 0, 1, 2, dot, 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 indicating that there is an infinite set of elements to be added which follows some kind of a pattern. So this looks like a way of listing out an infinite set, but you must understand that this is only an informal notation. This is not a formal notation. So you cannot write dot, dot, dot and claim that you are listing out an infinite set. So in fact, you need some other way of doing it, and we will come to that as we go along in this lecture. Now it seems reasonable that if a set is a collection of items, then we can collect anything and make it a set. It turns out that this is not quite true, and this is particularly a problem when we move to infinite sets. So we have seen some infinite sets of numbers like naturals and reals and so on, but in general, if you take an infinite collection of objects, it may or may not form a set. In particular, Bertrand Russell showed that there is a problem if we collect all the sets together and call it a set. So if we have a set of all sets, then we have a problem, and this is something which is called Russell's paradox, which we will discuss in a separate lecture. But you must be careful to note that though the notion of a set is intuitive and it seems natural that any collection of objects is a set, we have to actually be a little careful in mathematics if we are using sets in order to define what is a set and what is not a set. But given that, whatever we will see in our course will be fairly straightforward. So whenever we see a collection of numbers or a collection of objects of mathematical description, we can safely assume that they are sets. So again, some terminology. So we have talked of different things, items in a set, members of a set, and so on. So the most formal notation for the members of a set is an element. So a set consists of elements, and we write this membership of an element in a set using this E notation. So we have this E notation which stands for element of. So when we write X element of capital X, we mean that small x is a member of the set capital X. So for example, 0 is a member of the natural numbers, right? So this is what we use. So we can see, for instance, that 5 is an integer, but square root of 2, as we claimed, is not a rational number. So an element of symbol with a line across it means not an element of. So 5 is an element of the integer set, and square root of 2 is not a member of the set of rationals. So moving on from elements, we can compare sets by asking whether one set is included in another set, and this is called a subset. So X is a subset of Y if every element of X is also an element of Y, and this is written using this subset notation. So you have this familiar notation, X is a subset of Y. So for example, if we take just 2 out of the 3 players we had listed before, say Kohli and Pujara, then this set forms a subset of our original set, Kohli, Dhoni and Pujara. Similarly, if we take all the natural numbers and collect only the prime numbers, so remember that a prime number is a number whose only factors are 1 and the number itself. So it has exactly 2 factors, 1 and p, and then p is a prime number. So since many numbers are not prime, primes is a subset of natural numbers. Since the integers extend the natural numbers with the negative numbers, we can say that the natural numbers are included in the integers, so n is a subset of z. Similarly, we extended z to q, so the set of integers is a subset of the rationals, and the set of rationals is a subset of the reals. So if we wanted to draw it, we could draw it in this particular way. So we can draw a large circle representing the reals, a small circle inside right in the center representing the natural numbers, and if one circle is included in another circle, it means that this circle is a subset of the circle outside it. So here you can see that the natural numbers are a subset of the integers, and then from the integers we can say that they are a subset of the rationals, and the rationals are a subset of the real numbers. So this kind of a diagram where we represent a set by a boundary. So this is a very abstract diagram. We are not in this case, for example, listing out the elements of the set. We are just indicating the extent of the set, saying that the set R extends beyond Q and everything that is in Q is sitting inside R. So these are what are called Venn diagrams. So a Venn diagram is a very useful way to picturize a set and relationships between sets. Is one set a subset of another? Is one set not a subset of another? And so on. So we often use Venn diagrams pictorially in order to represent sets. So notice that every set is a subset of itself, because remember the definition of a subset set, that X is a subset of Y if every member of X is also a member of Y. So since every element of X is also an element of X, trivially, as an extreme case of this definition, every set is a subset of itself. So this in fact gives us an important notion which looks obvious, but it is not so obvious. When are two sets equal? So two sets are equal if and only if they are actually the same set of elements. So one way to check that two sets are equal is to check that everything in the first set belongs to the second set. So X is a subset of Y, and everything in the second set belongs to the first set. So Y is a subset of X. So often this happens when we have two different ways of looking at the same set of objects. We have two different descriptions of the same set of objects, and we want to check whether they are equal or not. Then using the first description, we argue that everything which satisfies the first description also satisfies the second description, and vice versa. So though this looks fairly obvious for finite sets, when it comes to infinite sets, we sometimes have to argue in an indirect way. So this, although it's an obvious statement, is very important, that X is equal to Y provided X is a subset of Y and Y is a subset of X. So sometimes we want to distinguish between the case when X is really a proper subset of Y, that is, it doesn't include all of Y, and that it is possibly equal to Y. So the subset equal to notation that we have, right, allows both. When we write X subset equal to X, what we are saying is that it is a subset but it's actually equal. So we are allowing both cases. So if we want to talk about proper subsets, sometimes we use a different notation. So we might either drop the equal to sign, just write the subset sign, or we might explicitly, like we said, not element of, right. So we are saying that this is not equal to. So we are dropping the equal to from below the subset. Now this is a bit dangerous. The second symbol, this not equal to, this is always correct. This is sometimes used both ways. So you have to be a bit careful when we look at books, when you see the single subset without the equal to, whether they mean subset and equal to or proper subset. So we know, for instance, that the natural numbers is a proper subset of the integers because the negative numbers are not there. Similarly, the integers are clearly a proper subset of the rationals, and because the irrational numbers are not rational, the rationals are a proper subset of the real numbers. So in most interesting cases, we will be looking at proper subsets. Sometimes we will emphasize it by adding this cross against the equal to, and sometimes we will not. And very often from context, we will know whether we are talking about proper subsets or we are talking about subsets which allow the full set. Now there is a very important set, just like the 0 is very important in numbers, there is a very important set which is important set theory. This is the equivalent of 0, it is the set which has no elements. So the set which has no elements is called the empty set and is written in this way. It is basically, you can think of it as a 0 with a line across it. Okay? So this Greek letter phi symbolizes the empty set, so it has no elements. Now what may not be very obvious is that this empty set is actually a subset of any set. Remember that we said that X is a subset of Y if every element of X is also an element of Y. Now you might argue that an empty set has no elements, so why is this true? Well, when we say for every and there is nothing in the set, then for every something is true, right? So if I say that all birds with 3 legs have pink beaks, then this is actually true because we can imagine that there are no birds with 3 legs and therefore every bird which actually has 3 legs will have a pink beak, but since there are no birds with 3 legs, this is actually true. So these kinds of vacuous statements, as they are called, will hold for sentences which use the word all where the set is empty. So in particular, every element of the empty set, because there are none, so every element that could be in the empty set is also in any set X that you build. So this empty set is a subset of every possible set. Now, though we have talked about elements and sets as though they are two different categories of objects, so we have numbers and the numbers belong to a set of the type n or q or r or z, a set can clearly contain other sets. So there is no restriction saying that the members of a set or the elements of a set must be some kind of discrete and indivisible objects. So one of the important sets of sets that we would like to look at is what is called the power set. So we talked about a subset. So supposing we want to enumerate all the subsets. So here is a 2-element set A comma B. So what are all the subsets? Well, we already saw that the empty set is always a subset, so that is one subset. The set itself, for any x, x is a subset of x, so x equal to AB. So we have these two subsets which come just from the fact that empty set is a subset of every set and the set itself is a subset. And then we have two proper subsets, either we can include the A and exclude the B, or include the B and exclude the A. So there are 4 subsets of X, and if we group together these 4 subsets into a larger set, then we get the power set. Now notice that this itself is a set, right? So we don't write, so this is different from this. The first is a set consisting of one element, namely the set consisting of the empty set. The lower thing is the empty set alone, which is a set with no elements. So if we put a brace around the empty set symbol, then we create a set with one element. So for instance, if you ask what is the power set of the empty set, right? So we know that the empty set has a power set which contains the empty set. So we have at least one empty set as one element of the power set, and there is nothing else, right? So the full set is also the empty set, but if we duplicate an element, it's the same thing. So in fact, the power set of the empty set is a set consisting of just one element, namely the empty set itself. So just remember this, that the empty set on its own denotes a set with no elements, but an empty set with a brace around it is not the same thing. It is a set consisting of one element, namely the empty set. So we saw above that if we have 2 elements, then the power set had 4 elements. So in fact, one can generalize this and say that if we have n elements, then we would have 2 to the n subsets. So for instance, if we had A, B, C, right, then we would have one subset which is empty, we would have 3 subsets which are 1 element each, and then we would have 3 more subsets which are 2 elements each, AB, AC and BC. And finally, we would have the set itself, right? So these are the only subsets. If you add these up, this is 8, which is 2 to the power 3. You can check that if you do it for A, B, C, D, then you would have 2 to the power 4, 16. So why is it that a set with n elements should have 2 to the n subsets, no more, no less? So here is one argument. Supposing we have n elements in the set. So let's just call these, without describing what they are specifically, as x1, x2 up to xn. So we have n distinct elements x1 to xn. Remember, these must be different because you can't duplicate elements in the set. So now we want to construct a subset. So how do you construct a subset? Well, for each element xi, we have to either include the set, include xi in the subset, or exclude xi from the subset. So we have to make a choice for each xi. Right? So overall, we have to make n choices. Right? For each xi, we have to decide whether to include it or exclude it from the subset. So we have two different choices for each element. So we have two ways to decide whether to do something with x1, keep it or leave it, x2, keep it or leave it. So then we have 2 times 2 choices for x1 and x2 together, 2 times 2 times 2 choices for x1, x2, x3 together. So in general, if we have n such choices where each choice involves 2 options, then we have 2 into 2 into 2 n times 2 to the power n choices. So each of these choices gives us different subset. So whenever we make a different choice, we will either leave out xi from the set or put in xi, so it will differ from the choice where we do the other thing. So each choice generates a separate subset. So there are exactly 2 to the n subsets. Here is another way of looking at subsets and getting to the same result. So we can actually think of subsets in terms of binary numbers. So let's again think of our n element set x1 to xn, right? So now supposing we look at n digit binary numbers. So digit actually comes from decimal. So we say bit for binary digit. So n bit binary numbers. So remember, in a binary number system, we have zeros and ones, and the place values represent powers of 2. So we have the units digit is units as usual. The next digit 2 to the power 0 is number of 2s, number of 4s, number of 8. So it's like the decimal thing is in base 10, this is in base 2. So now if we look at n bit binary numbers, then for instance if we look at 3-bit binary numbers, then we have 8 of them. We can start with 000, then 001, 010 and so on up to 111. And again, the reason that there are 2 to the n-bit numbers is because for each bit we can choose to put 0 or 1. So we have 2 choices for the first bit, 2 choices for the second bit and so on. So it's not surprising that an n-bit binary number can represent 2 to the n different values from 0 to 2 to the n minus 1 if we think of them as numbers. Now we are interested in n-bit binary numbers as representing subsets. So what we will look at is the ith bit and say that the ith bit represents the choice that we made. If we chose to keep xi in our subset, we will call it 0. If we chose to, we will call it 1 for example, and if we choose to omit xi from our set, we will call it 0. So 0 represents the choice where we leave out xi, 1 represents the choice where we keep xi. So supposing we have this 4 element set A, B, C, D, then if we look at the binary sequence or the bit sequence 0, 1, 0, 1, the first 0 corresponds to A, so it says leave out A. The second 0 corresponds to C, so it says leave out C. And for B and D, we have put a 1, so it says keep B and keep B. So it says leave out A, keep B, leave out C, keep D. So this 0, 1, 0, 1 as a binary sequence corresponds to the set B, D. What does 0, 0, 0, the all 0 sequence say? The all 0 sequence says every xi in the set is omitted from the subset. So this is precisely the subset which is the empty set because it has no elements. And what about the all 1 sequence? Well, the all 1 sequence says every xi that we have is included in the final subset. So this is the set itself. So remember that these are the two extreme subsets, the empty set and the set itself, and all the other ones come in between. So from this we can see that every n-bit number represents one sequence of choices. So this gives us 2 to the n choices because there are precisely 2 to the n-bit numbers. So hopefully with this you are now clear about the fact that any finite set with n elements has exactly 2 to the n subsets.